This is Chapter 12, Introduction to Organic Chemistry and Hydrocarbons. We're going to start with Section 1, which is Organic Compounds. Organic chemistry is the study of carbon-based compounds, and these compounds tend to have many properties in common, such as this vegetable oil here, which is insoluble in water. In this section, we're going to learn some of these properties and how they are different from the properties of inorganic compounds. In order to understand the properties of organic compounds, we need to know their composition and structure. As I said, organic chemistry is all about carbon-based compounds, and these usually contain large amounts of hydrogen as well. This is where the term hydrocarbon comes from. But they can also contain other elements, usually nonmetals such as oxygen, sulfur, nitrogen, etc. While organic compounds have many properties in common with each other, there's also a lot of diversity among them, and so they can be found in a wide variety of substances such as gasoline, shampoos, plastics, perfumes, and most pharmaceutical drugs. Organic chemistry is also the basis for all life on the planet as we know it. We can organize organic compounds into different families or classes based on their functional groups. A functional group is just a collection of atoms that are bonded in a specific pattern, and compounds with the same functional group will share some properties in common. So what are the properties of organic compounds? Well, we know that they're all covalent molecular compounds, and this is because they're based in the chemistry of carbon. Carbon is a nonmetal that has 4 valence electrons, and so it's relatively difficult to form an ion from carbon. Instead, it would prefer to share electrons and form covalent bonds. This also can help to explain why these compounds are usually not soluble in water. That's because most of the bonds in an organic compound are either carbon-carbon bonds or carbon-hydrogen bonds. Both of these are nonpolar bonds, and so the molecules overall tend to be very nonpolar. From the solubility rule, like dissolves like, we would predict that these would not dissolve in water. This also explains their low melting and boiling points. Since they're nonpolar compounds, the intermolecular forces causing them to stick together into the liquid or the solid phase are just weak dispersion forces. That means it's relatively easy to pull them apart, to liquefy or vaporize them, leading to low melting and boiling points. And finally, we know that organic compounds are also flammable in that they can be burned in the presence of oxygen to produce carbon dioxide and water. This chart compares the properties of organic and inorganic compounds using C3H8 propane as an example of an organic compound and sodium chloride, NaCl, as an example of an inorganic compound. As you can see for propane, it's a covalent compound, it's nonpolar, it has very low melting and boiling points, it's flammable and insoluble in water. It has all the properties that we just described. Sodium chloride, on the other hand, has basically the opposite properties, right? It's ionic, where propane is covalent. The polarity of the bonds is ionic instead of being nonpolar. This leads to a high melting and boiling point, and it can't burn or combust in the presence of oxygen. And it can dissolve in water, because the water molecules are able to disrupt the ionic bonds. So if you know the general properties of a compound, you should be able to predict, or at least make an educated guess, as to whether it's inorganic or organic. For instance, the first description here is that it contains carbon and hydrogen atoms, and we know that that's the definition of an organic compound. For B, the description is that the compound is not soluble in water. Again, this would indicate that it's a nonpolar compound, which is usually a property of organic compounds. If a substance has a high melting point, however, that's usually an indication that it's inorganic because it's made from a lot of strong ionic bonds. If you have the formula of the compound, it's easier because you can just look for carbons and hydrogens. This one has no carbon, so obviously this is an inorganic compound, magnesium chloride. And the last one is if a substance burns easily in the air, that's a very good indication that it is an organic compound undergoing combustion. Since carbon is central to organic chemistry, it's important to understand its bonding patterns. Carbon is in group 4A or 14 of the periodic table, which means it has 4 valence electrons. Each of these electrons can be shared with an electron from another element to form a covalent bond. So carbon typically forms 4 bonds. These may be 4 separate single bonds or a combination of single, double, and triple bonds in different patterns. But either way, it'll be a total of 4 bonding pairs to make an octet. For example, methane, CH4, has a central carbon atom with 4 single bonds to 4 separate hydrogen atoms. There are many ways to represent an organic compound like this, and you can see a few different examples here. The first 3 are 3-dimensional representations that try to show the real shape of the molecule, while these last 2 are simple 2-dimensional pictures that just try to show the bonding patterns or connections between atoms. We'll look at each of these kinds of models in more detail in a moment. Methane is the simplest hydrocarbon, so we'll use it as an example to illustrate the different types of models that we can draw. If we were to draw a Lewis diagram for methane according to the rules we learned a few chapters back, we would end up with something like this. In organic chemistry, these can get much more complicated, and so a picture like this, which explicitly shows every bond within the molecule, we usually refer to as an expanded structure. This picture, on the other hand, is called a condensed structure because it doesn't show the carbon-hydrogen bonds explicitly. Instead, the hydrogens attached to a particular atom are just written next to that atom, and we have to understand that they're really attached through single bonds. Since methane is so simple, the condensed structural formula you see here is pretty much the same as the molecular formula that just lists the atoms, CH4. But that's not always true in general. That brings us to the 3D models of methane. To draw these correctly, we have to remember how electron groups arrange themselves according to the valence shell electron pair repulsion theory. For an atom that has 4 separate atoms attached to it and no lone pairs, the shape around it is going to be tetrahedral with bond angles of 109 degrees. Picture A depicts this with a space-filling model that shows the atoms as spheres just stuck together. Picture B is a ball and stick model, which is similar but has more separation between the atoms, and so it shows the bonds as rigid sticks or rods connecting them. Picture C depicts methane with the wedge and dash bonds to approximate the 3D shape, as we saw in the previous chapters. And this is the most common way to draw the 3-dimensional structure of a molecule because it doesn't really require any special artistic talent. Now that we've seen these different kinds of models, we can look at the next smallest hydrocarbon, ethane, or C2H6. In this molecule, we've simply replaced one of the hydrogens in methane with another carbon, and then added 3 more hydrogens to that to give it a total of 4 bonds. In most organic molecules, the carbons all form a continuous chain like this, with the hydrogens attached around the outside to satisfy the 4-bond requirement for each carbon. This expanded structure is probably the easiest way to draw organic compounds at first because it's more or less an extension of the Lewis diagrams we're familiar with. Condensed structures are theoretically even easier to draw, but when you're first learning this, it can be easy to misplace hydrogens or lose track of the correct number of bonds going to each atom. These 3-dimensional structures show how the tetrahedral geometry of methane extends to longer chain hydrocarbons. Each carbon in the chain has 4 atoms attached to it, so each is the center of a tetrahedron. That means if you're using the wedge and dash bonds, like in C, you'll need to show them for every tetrahedral carbon in the molecule. Of course, the shape is a little easier to see in the space-filling and ball and stick models here, but you'd usually use some kind of software to construct those. This is a simple problem to help you understand how to think about the 3D structure of an organic molecule. It says to predict the shape around each carbon atom in a molecule of butane, C4H10. To answer a question like this, you need to consider each atom on its own. You can see that this carbon has 4 atoms bonded to it, 1, 2, 3, 4, and no lone pairs, so it must be tetrahedral. But the same goes for all of these other carbons as well, so they must all have a tetrahedral arrangement. This shows what it looks like when you draw that arrangement out using the wedge and dash bonds to indicate the overall shape of the molecule. We'll see later that you can rotate around these bonds and twist the molecule into different shapes, but for now it's important to note that even when it's stretched out as much as possible, there's still this zigzag pattern to the carbon chain because of the bond angles imposed by the valence shell electron repulsion. Here you see a 3D model of the same molecule in the same initial orientation, but you can rotate it around in 3-dimensional space to see how the zigzag pattern arises from the tetrahedral arrangement around each individual carbon atom. I'll post a link to this model in the description so that you can see for yourself.